Okay, so today we're going to continue where we left off, our discussion on MongoDB, and of course I'm using the set of slides that are heavily influenced by the Mongo University slides, so you can use this as a resource to go through the certification yourself. So we last left off on Chapter 4, Part 4, talking about query operators. If you might recall, we covered query operators, and again, this will be available in the video recording of last lecture, but just to bring us up to speed for today, we left off at looking at comparison operators, at logical operators, and even array-based operators. And actually, we left off in the middle of array-based operators. So we had just looked at how to go ahead and define projections. So a projection is a second parameter that we can pass to our find method such that it can filter out any unwanted fields that we don't want, or filter just the fields that we do want. So we had showed an example of, on this projection, I want to find on the fields of amenities, those amenities that are only of array size 20 and that include internet, Wi-Fi, kitchen, and heating inside of their group of amenities. So it has to include these four and have a size of 20 in order to be part of the cursor result, the documents that are found from this call. And then the second parameter here is the projection. So when we get back our cursor of documents, we will only contain the fields that include the price and the address. And so also by default, ID is always a field that's included with that, unless I put ID, underscore ID, to be 0. That's one time I can mix and match ones and zeros inside of my projection object. Okay, so we had left off there. And so we were about to discuss another array-based operator that we can use for as a query operator, and it's one that's called LMMatch, short for element match. And so this operator matches documents that contain an array field with at least one element that matches the specified query criteria. And so our basic syntax for this is we would have an object or query object. The field would be, well, whatever the field is that we want to try to go ahead and match on the array. And then inside of the object on this value, we would have our operator. And so this would be an element match, and then this itself would have an object that uses a field value pair, which is going to be the element we want to try to match to. And so let's see if we can't just look for an example of that. So no, not there, not there. This is what I'm looking for right here. So an example of how we might use the LMMatch would be on this query. So for this query, the intent is to find all documents where the student in class 431 received a grade higher than 85 for any type of assignment. So let's see, we have our current database, and so we're going to look at our grades collection. On our grade collections, we want to find, and let's see what we're doing here. We have our query here. So we're going to find this student or all students in whatever class is 431. So we're filtering a cursor with that. And now notice the second parameter here is our projection. So we can use LMMatch not only in a query in the first parameter, but we can use all of these operators also in our projection. So inside of our projection, we want to project on our scores array. So this is the first field, this is the array field, and then the query field that's going to use the LMMatch will have the operator LMMatch, and the field is also going to be the score field. And the criteria in which we want to match an element is if the score inside of scores is greater than 85. And then any any student who has a grade of higher than 85 in any of their scores will then be returned inside of that projection, or we'll turn the scores of that inside the projection. Okay, so alternatively, so in this example, we saw how to use LMMatch in a projection. In this next example, I want to show how we can use LMMatch inside of our query. And so very similar logic here. Here, we're going to find all students where the student had extra credit score. So inside of our current database, we will go ahead and access our collections that is called grade. From our grades collection, we will try to find, and again, the intent of this is to find a student who has a extra credit score. So we will look at the scores field, and inside the scores field, we want to do an element match because this is an array. And so we want to element match inside of each score. There is a type. So so scores is an array of objects where one object is a score and the other is the type of score it is, whether it's a quiz or homework or extra credit. So here we want to element match every score object that is of type extra credit. Excellent. Okay, and then just looking at the previous examples that I skipped by, these are probably from earlier in the lecture. So let's visit those now from previous lecture. So in this instance, and we probably looked at an example similar to this. Here we would want to find all documents with exactly 20 amenities, which include all the amenities that are listed inside of our query array, and display and project the price and address. So essentially what this query is doing is, from my current database, I have a collection that's called listings and reviews. This listings and reviews is probably inside of the sample Airbnb database. So from the listing and reviews of Airbnb data, I want to find all of the documents, all of the listings where the amenities has the array size of 20, so there's at least 20. Oh, there is exactly 20 amenities, and I want to find all documents that include internet, Wi-Fi, kitchen, heating, family, kid-friendly, washer, dryer, essential, shampoo, hangers, hair dryer, iron, and laptop-friendly workspace inside of that collection of amenities. And so this is the first parameter inside of my find. So this is my query object. And then my second parameter here is my projection object. So the returning cursor will only include the price and the address. So it helps filter out the fields that we do not care about in our results. And then the other example here is just a simple projection where here we will, on our current database, also look at that same listing and reviews collection, and we want to find very specifically just the amenities that include all amenities that include Wi-Fi. So recall that amenities is an array, but when we only have one element, we can just go ahead and do that as we would if it were a non-array based field or value, I should say, a non-array based value. So we only have to use all or LMMatch if we want to search for either more than one item inside of an array, or if we want to go ahead and do some kind of evaluation on the values inside the array. So here we're just matching to one item, and then we're just doing a projection here. And so here, this was that one edge case of a projection where we could have a mix of zeros and ones. In this instance, we want to show the price and the address, but we do not want to show the ID, which is what displays by default. Okay. And so we talked about that. Okay, so let's do a quick little quiz here. So suppose that we wanted to define an array query that finds how many companies in our companies collection that have offices in the city of Seattle. Now, presumably a company each company could have multiple offices, so that will be an array of likely objects. And so if we want to define such a query, we would first start with DB. So given our current database, we have a company's collection. From that collection, we are going to want to find, and let's see what this query is. So we're going to want to find the field of offices. But since offices is a collection, since you can have more than one office, we want to element match the office that has a city field where it's Seattle. And since I want to find how many companies, I will take the result of this cursor that I get back, the result of that, and I will query its count. Okay, let's see if we can follow up with another problem that we might try to solve here. So which of the following queries will return only the names of companies from the companies collection that had exactly 8 funding rounds? And in this instance, we want to choose the best option. So one of these 3 is going to be the answer. So let's look at this first one. So from my current database, I have a companies collection. From my companies collection, I want to find, and here I am passing in a query. So the query is going to check the funding rounds. And so here the funding rounds is going to be an array. And so I'm going to find where it's exactly 8. So here I can use the size operator to find when the array is exactly 8 elements. Okay. And so here, which of the following queries will return? And so here the idea is I need to return only the name of the companies. And so that means I also want to use a projection. So looking at the projection, the second parameter here, the name. So whenever I use a 1, that's going to be in the cursor. Anything that's not inside this projection then will not be part of the cursor. So that returns the name. And by setting ID _ID to 0, it will not show the ID either. So yeah, this looks like this is a good query for exactly what this problem is highlighting. But for completeness sake, let's look at the second and third options. So in this database, I'm going to go ahead and access the companies collection. I'm going to try to find from that. Here, I'm going to do funding rounds, okay? And so I'm going to, on the field of funding rounds, find just the ones that have an array size of 8. So this is the appropriate query. This looks right. But my projection here is putting name to 0. So this means it's going to show me everything except for the name. That's not what I want. Oh. And then looking at this third one, I have this database, and we're looking at the companies collection, and from it we want to find, and again, this looks correct. The funding rounds include only those funding rounds that have the size of 8, but on the projection, even though I am including the name, I'm not omitting the _ID element. So this will actually return a cursor that includes the name of the company and the ID. And so here we explicitly said we want to return only the name. So the first option will be the best out of these 3. And indeed, we see that is the case. Okay, so let's talk about array operators and how they relate to subdocuments. And then we'll be done, I think, with part 4. Okay. So when we query arrays or subdocuments, so this is true for both cases, the Mongo query language, or what we call MQL, can use dot notation to specify the address of any nested element within a document. So to use dot notation in arrays, we specify the position of the element in the array. And so we'll see examples of that in just a moment. So to give you an example of how this might look, we would have our current database. From our current database, we'd have whatever the collection is. From the collection, we would go ahead and we're trying to find something. We're trying to query from it. We have our query object. Here, I can have whatever the field is, and then I could put, let's suppose it is an array that I'm trying to dereference something from, then I could use the index as one of the properties that I'm dereferencing, or I can use the, if it is a subdocument, I could use the nested field for that subdocument. Let's look at a maybe better example to see, or an actualized example of this dot notation, because that might make a little bit more sense. So again, we use this dot notation to be able to use it to, in a query, to access fields in a subdocument. So suppose I have this trips collection. So in my current database, I have the trips collection. From the trips collection, I want to just find one document. Here, I'm going to find the document such that I have the field start station location, but inside of start station location, if I look here, this is the document example. Let's see, this document has an ID. It has that start station location, which the value of that is an object itself, and that object, or that subdocument, it's a document itself. So that subdocument has a collection of field values. From those fields, I can say, oh, I want to access the type one. So inside of my query, I could say start station location dot type, and that allows me to access the type fields from the start station location field. So dot notation works just like it does in any kind of common programming language to dereference one thing that's contained inside of another. Okay. And so then this is then just doing a match for us. So this is going to filter out or find the start station location type that is point. And so here, just another example of how this might look is if I had my field one. So this is my field one. I can then do the dot notation to access that other field. And then if inside that other field was an actual subdocument itself, I could do dot also a field. So here I have two dot operators and three different fields. My fields for my document, my subdocument, and my subdocument. And we can resolve all that to match on this value inside this subdocument. Okay, so recall that we can use dot notation not just for documents inside of our collection, but we could also use it on array values. So we use index numbers, which may be used in dot notation to access a specific position in an array from our query. So say, for instance, we want a position of 0 at index 0, which is the first position of an array element. Then our query might look like this. From our current database, we want to access the companies collection. From the companies collection, we're going to find some documents. The query in which we're going to find these documents will be from the relationships field. This relationships field is an array. So if I want to index a particular indice of that array, so if I know that the array is ordered in some specific way, let's say, for instance, inside of companies, inside of relationships, the 0 index is always the CEO, and the index 1 is always the CTO, and the index 2 is always the CIO, and the index 3 is always like, I don't know, the HR director, right? So if you know the ordering of that array, then it might make sense then to say, well, for this field, I want to always look at the CEO index of the relationships. So I want index 0. And then index 0 might be an object itself. It's an array of objects. So I might want to access the person field of that object. And from that person field, that might also be an object that includes like a first name and a last name. So I want to access the last name. And then I want to pattern match. So I want to match all the way through this. So from this array to this position, to this subdocument, to this subdocument, I want to match on the value of Zuckerberg. And so this would represent my query object using dot notation to dereference things from both arrays and subdocuments. And then here I'm going to do a projection that will include just the name and the ID. Okay, another thing we can do in terms of doing these MQL queries, we can also do regex as a operator for matching. So we could also build out a query that matches on just the term CEO if I wanted to. So that is another kind of tool in your toolbox of query building that you have access to. So just to quickly go over this, suppose we had this problem. We want to write a Mongo query language query that finds how many trips inside of the sample training database with the trip collections, with the trips collection. Let me make this more evident that this is the name of the collections. Okay, so inside the trips collection, which is inside the sample training database, we want to write how many trips inside the trips collection started at stations that are to the west of the -74 longitude coordinate. So one note for us is that longitude decreases in value as you move west. So what might our query look like in that regard? Well, so let's see. If we had our current database, we want to access our trips collection. From it, we're going to want to find. And so here, we're going to want to use the field of start station location. And so the start station location itself has a subfield, which is coordinates. So I want to access the coordinates field of the start station location. And from it, I want to find those instances where the coordinates is less than -74. And since this is asking me how many trips, then I want to call the count on that resulting cursor object that's returned from that query. And so I would know that start station location has a coordinates attribute by actually being familiar with the schema of the database. So again, when you're going through the Mongo University courses at any time, you could just go look through Atlas, or you can just go ahead and do a find one on DB trips to see what exactly it has on it, so that you know how to what you should be dereferencing. Okay, so suppose we had this other problem. So write a query that finds how many inspections from the inspections collections were conducted in the city of New York. So what might that query look like? Well, here we can just go ahead and we would, from our current database, which would be inspections, we would want to find, and our query that we're going to find is, well, there is an address field. Inside each address field is a city. So I want to use that dot notation to access the city field of an address to find out when it's equal to New York. And again, since this is asking me how many of these inspections occur, I'm going to invoke count on the resulting cursor. And then let's do one last kind of quiz on these queries, just to make sure we kind of have a firm understanding of them before we move on to the fifth part. So here, which of the following queries will return the names and addresses of all listings from the listings and reviews collection where the first amenity in the list is the internet? Okay, so I can look at, okay, so here I have my database. I am accessing my listing and reviews collection. I'm going to do a find here. I have amenities, and remember that is an array. I want to access the first amenity, so that's going to be at index 0. I'm going to do dot notation, but $0, that is not correct syntax. That's not how we dereference, use dot notation to get the 0th index of an array, so it's not going to be that. I'm going to jump down to this third one and see, well, this one is trying to use box notation, square bracket notation. Well, that's not the syntax we use either. Here, it's just amenities dot and then the index number, right? There's no symbol that's used for accessing the index number. It's the numerical index is treated just as if it were a field name in and of itself. So it's just the index number. So this is the appropriate one. This option B. Excellent. And so now we're done with part 4. Let's move on to part 5, indexing and aggregation pipelines. So we talked a little bit about aggregation just briefly when we were doing the expressive operators last lecture. We'll talk more about it this lecture, much more in this lecture, an entire part on it. Okay, so in this section, we'll talk about the aggregation framework and then the ability for sorting and limits on the cursor. We'll also introduce the concept to indexes. We'll introduce the concept to data modeling. And then we'll talk about upserts, which is essentially both an update or an insert, depending on what it needs to be at that time. So let's look at an aggregation framework. So here, our aggregation framework in its simplest form is just another way to query data in our Mongo database. So far, in the other 170 slides or so, we looked at MQL, right? We looked at being able to access data from our database using the MQL syntax. Well, the Mongo aggregation framework is just an alternate way to be able to get data, but it's a more powerful way of accessing data. By more powerful, recall, we've already seen an example of an aggregation framework kind of in with the expressive operator. But we're going to formalize it much more so in this section, though. So let's look at the syntax differences here. So suppose we wanted to find all documents that have Wi-Fi as one of the amenities and only include prices and addresses in the resulting cursor. So the traditional way we would do this using MQL queries, using the way we've discussed for the last 2 lectures, would be this way. From our database, we have this listings and reviews collection. From it, we want to find, right, that's our query. We want to find from it our query object and our projection. So we want to match when amenities is Wi-Fi, yeah, and then we want to project, include the price and address, so we want to project the resulting cursor to have the price and the address. And since we only want price and address, we will set ID to 0. And just so that this looks pretty, we'll do adopt pretty on there, but that's not necessary. Okay, so if I wanted to do this using the aggregation framework, instead of using the find keyword, I would group all of the query objects I want to perform together inside of an array. And so this allows me to have very complex queries, to aggregate, hence the term aggregation framework, to aggregate a collection of queries and pipe one into the other, into the other, into the other. So to effectively just show you an example of an aggregation query that does the exact same thing we did before, let's take a look at this. So from our current database, we have our listings and reviews collection. From it, we want to create an aggregate query. So inside of an aggregate query, it's always going to be an array of query objects. So we'll use our box notation to go ahead and create an array. And the first query object will be a match operator, where it will match amenities to Wi-Fi. And our second query object will be a project query. So here we're going to use the operator project, and we want to project price and address and remove ID. So these do exactly the same thing, just slightly different syntax. And again, our aggregate method uses arrays, so highlighting the fact that this uses an array of query actions. And again, the concept of what happens here is the aggregation framework works as a pipeline that passes the results of one query to the next in the array of queries. And so because of this, the order of the actions does matter, because it's performing the first query action followed by the second, followed by the third. So you could think of it as something like this in terms of a diagram of this pipeline. So in the example we just gave, where we do a match of amenities to Wi-Fi, and then we do a projection that includes price and address and not ID, then this is what it would look like. We have the entire collection of listings and reviews, and then we're going to perform this match operation that's only going to produce the documents that have Wi-Fi, and then we'll do this project operation that will then just create a cursor that only includes the price and the address in each of those documents. Now, why might we want to use this aggregation framework as opposed to MQL? Because it's far more expressive. It allows for far more complex queries, but not just that, we have more power in being able to define the shape of our data or the grouping of our data or being able to compute on our data using this aggregation framework and what we can use with MQL. So recall that MQL has the ability to filter or to update documents. But with aggregation, we get additional methods that were not available to us before, additional operators, the ability to group data, to compute, or to reshape. So this is the big thing. With aggregation framework, we can compute and reshape our data between each query action that we do. So effectively, we can do everything we could do in MQL, right? We can use aggregation to also filter and update. But we can't do grouping with MQL. So let's talk about grouping, since that seems to be one of the things that the aggregation framework gives to us. The group operator is an operator that takes the incoming stream of data and it siphons it into multiple distinct reservoirs. So it allows us to reshape the resulting data. And so non-filtering stages of our aggregation framework, of our aggregation query, do not modify the original data. So it just works with it as a cursor, just like MQL would. So on the match operation that we saw before, it treats the data as it normally would. But if we then did a group operator on it, then this can actually change the shape of the data for the next query action we want to perform. Let's talk about the syntax of this group operator. So this might make more sense. So all group operators are essentially a query object, just like all the other actions we've seen inside of Mongo. So the operator name would be group. Since it's an operator, it's prefaced with the $sign. The value of a group is itself going to be a document. It has to have a ID field, and then whatever, which will represent the ID of how we're grouping things, grouping documents. And then we have to give it a concept of how we're grouping them. What field are we using to group them by? And so that's going to be our group by expression. And we'll look at examples of that in just a moment. And then we can have, when we group things, we can have actions that we bind to the grouping. Again, we're going to see examples of that, but that's what this here is highlighting that we could do. So like we could have, say for instance, a sum attribute or a count attribute or something like that. So to give you a more distinct example, an actual implemented example, because I find that always helps. Suppose we have this query we want to get done. How many distinct countries have listings, and how many listings does each country have inside of our Airbnb database? So imagine we have our current database, our collections of listings and reviews. On this listing and reviews, we want to do an aggregate query. So that takes in an array of query actions, or query objects. The first is going to use the project operator. So notice we can actually project first. And here we're going to project based off of address and ID. So we've changed the shape of our data in some way by projecting it. We're filtering out everything besides the address. So now the next action we're going to do inside this query action is going to then group. We're going to group where we're grouping based off the idea of the address country. So this will regroup all of our documents into these collections that are based off of giving the ID as their address, their country address. And then each of those documents will have a count field, right? The result of this group will include a count field that will give you the sum of that grouping. Okay, so let's look at exactly how this might actually play out to step by step. So suppose here, with my group operator, my sum operator, suppose that I had here a group operator where I am grouping based off of category. So there's a category field that's going to be the ID for the group. I'm going to create another field inside of the resulting document that will have a total that's going to use this sum operator that's going to look at the price field, and it will sum the price fields of everything that it gets grouped by. So that's essentially what's happening here. Is when we group, we're defining a new shape of our document where it's going to group by this as our ID, and these are additional fields it's going to apply to it. So let's look at our original set of documents. So this group operator would apply on this set of documents. But these documents might have multiple fields. The ones that we're grouping by, though, is based off of category and price, because that's going to be what the total field is going to be. So let's see, we have a category fish. Well, since we're grouping where the ID is category, these two things are going to get grouped into the same document, because anything with the category of fish are essentially having the same ID. And so when that happens, we take the price of this and the price of this, so 5 and 7, and we're going to sum them together. So the ID and the result of this group operator, I will have an ID of fish that now has a total, right? This total of 12. Now, inside this example, I also had a category of meat. There's only one category of meat, so it gets grouped by itself. It has an initial price of 25, so of ID meat, the total is 25. And so that's an example of how we can use a group operator inside this aggregation framework to change the shape of the data, which means like redefine the set of fields or even redefine how we're grouping or clustering data together and how we're labeling it. And then even providing new sets of fields based off of that grouping action, such as like summing some field together. Okay. So a quick summary of just the aggregation framework is it's more powerful than just MQL. It allows us to define pipelines or allows us to stage the order of multiple query actions. And the syntax is slightly different than traditional MQL. And so we won't go too much into detail with aggregation frameworks here. Just wanted to highlight some of the possibilities. Now, I will say that Mongo University on their website has a number of different certification courses. And I believe they do have a certification course dedicated just to developing aggregation queries or aggregated queries. But for this course, we're only going to worry about the Mongo basics. So with that said, let's move on to just some examples of these aggregation calls. And most of these I think we've already seen. So this was the first example where we're matching and then projecting. And then here, I think we've already seen this where we're projecting on the listings and reviews collection, the Airbnb data. So we're projecting just the address, and then we're going to group by the address country. And then here is another one where, in addition to addressing by the address country, we're also going to produce a count where it'll be sum, and it provides a value of just 1 for each thing that it matches when it groups by. And that'll give us a count of each thing that gets grouped together. Okay, so if we wanted to try to demonstrate our ability to do an aggregation query ourselves, suppose we had this problem. We want to write a query that finds all the room types that are present in the sample Airbnb listings and reviews collection. So if I wanted to do that, well, from my current database, I have the listings and reviews collections. I'd want to call an aggregate function, which is going to take in an array of queries. And here, the only query I want to do is the one operator that I don't have access to inside of my MQL, inside my Mongo query language, which is that group operator. And I want to group all of the rooms by their room type. So the ID for grouping is going to be room type, and that'll return just the types of rooms that are available to me. And in fact, let me see if I can't. So here, if I want to do that, do I have? Let's see here. Let's use, okay, so let's check DB here. Okay, So let us see if I go ahead and make this query from DB inside my listings and reviews. I'm going to call this aggregate, where I'm going to do a group operation on room type. It's going to return to me this new collection, right, reshaped data, where the only field in there is that ID, and then this the room type as the ID value. So there's 3 different room types. There is an entire home, apartment, private room, and shared room. Okay. Suppose we have this problem. Oh, let me also put here in case I get questions. Okay. What are the differences between using aggregate and find? Well, aggregate allows us to compute and reshape data in the cursor. This is true. This is one of the powerful things about it. Find can do what aggregate can do and more. Nope, it's the opposite of that. Aggregate can do what find can and more. Yep, it's going to be that. And find allows us to compute and reshape data in the cursor. Nope. So it's going to be A and C. Okay, let's talk about some more cursor methods. So we know 2 cursor methods already. That is pretty and count, and we've been using that since like part 2. But now let's look at some more cursor methods that allows us to limit the number of values in a cursor, or to be able to sort the documents inside of the cursor. So again, this will then open our syntax and cursor methods up to be 4. We can count. We can make the printout of the document to be pretty. We can limit the amount of documents in the cursor. We can sort them. Okay, so let's talk about the sort method. So we call that on the cursor. So that's the return from a query, just like count and pretty are done. So here, imagine in this example, we have a current database. Inside our current database is the zips collection. Inside of the zips collection, we will do some kind of find operation. On the result of that find operation, we'll return a cursor of documents. Suppose we want to sort those documents. And we want to do a complex sort, so we want to sort based off of 2 different fields. Well, when I sort, I can pass in a object, a document that defines how I want to sort. So my sort object here will give the field that I want to sort on, and if I pass in the value of 1, that means I want to sort them in increasing order. If I provide a -1, then I want to sort in decreasing order. In this situation, order does matter, so we'll sort based off of population in increasing order. And on the occurrence that there's more than one population with the same value, then it will then sort city by decreasing order. And so let's talk about limit. We can actually use limit without sorting. So limit takes in a parameter. It's the number of documents we want to limit it by. So an example of how we might use limit without sort is, imagine if we do a find, and our find might produce, let's say, 20 documents. It could produce 30 documents. It can produce many documents. If I apply limit, I can limit the number of documents to a smaller number, to a set number. So instead of returning X amount of documents, I will limit it to the 5 documents. Now, clearly, it makes sense to use limit and sort together because this allows us to sort the documents based off of some criteria, like let's say the top 5 highest prices, and then I limit it, or the top prices. So I might sort based off the price, and then I limit it to 5, and that would give me the top 5 highest priced Airbnbs, for instance. Or if I sort in reverse order, give me the top lowest Airbnb residences. So I can use limit and sort together. And so the big thing to understand is I don't have to use limit and sort in any order. I can limit and then sort, or I can sort and limit, and they give me the same behavior. So order doesn't matter. A cursor with limit.sort means the same as sort.limit. So just some examples of how this might look is, so imagine inside of my current database, I have a zip code collection, and I want to find something from it. After I find it from the resulting cursor, I can then sort based off the population and increasing order, because that's what the 1 means. I will then limit it to the top one. I could do the opposite of that. I can do it in decreasing order and then do it in the limited to return just the lowest one. Or I can do the top 10 of the lowest ones, or I can do multiple fields for my sort. So population, and then if the population is the same, do it based off the city. Okay, so let's see if we can't quiz our understanding of sort and limit. Relatively simple concept. So suppose we have this problem. Which of the following commands will return the name and founding year of the 5 oldest companies collection? So here, and I want to do all that might apply. So let's see here. I have the current database. I have the companies collection. I want to find from it. So I'm going to do a query where the founded year is not equal to null. So I'm going to do some filtering. I'm going to take those instances where perhaps maybe the founded year isn't defined because it's not known. So I don't want that to be part of the sort. So I'll make sure to return only those documents that have a founded year. Okay. And then since I want to return the name and founding year, I'm going to do a projection. So second parameter is I'm going to have the cursor only have the name and the founded year. Okay. And then from this cursor, I'm going to sort founded year in increasing order. So it'll be lowest to biggest. And I'm going to limit it to the top 5. And so, yeah, this does that. This is the a command that returns the name and founding year of the 5 oldest companies. Okay, let's look at the second one. So from my current database, inside my companies collection, I'm going to do a query on founded year such that it's not equal to null. Okay, on my projection, it's going to be name and founded year. Okay, and then I'm going to limit to 5. And I'm going to then sort those based off of year. And so this is really doing the same thing that A is doing. It's just reversing the order of limit and sort, and that doesn't matter for us. So this is also correct. A and B is correct. Let's check this other one. Oh, this is not doing a query at all. It's just doing a projection. So anything that might have a null will populate to the top. So this isn't going to probably produce the result we're looking for. We'll probably get things that have null founded years, and that's not going to be the oldest companies. So it's not going to be C. And then let's look at this one. On our database collection, on our current database in our companies collection, we're going to find, and here we're doing what looks like it's supposed to be, we're just doing what our projection is as our query. So our result is going to display a lot more things. And so also, yeah, so this isn't going to, it'll try to match on this, and we probably don't want to match on that. This is supposed to be our projection, not our query. So it's just going to be A and B in this instance. And yep, that is indeed the case. Okay, let's try another problem. Define a query that finds what year was the youngest bike rider from the trips collection born. Well, if I wanted to try to define that, I might build a query that looks something like this. From my current database, inside of my trips collection, I want to go ahead and do a find. I'm going to do a find where I'm searching. I'm going to sort on birth year, but I want to do just like I did in the previous example. I want to make sure that there is a valid birth year. So I'm going to only get back those documents where the birth year's value is not equal to an empty string. And then I'm going to do a projection to show just the birth year. And then I'm going to do a sort where the birth year is in decreasing order, and I'm going to limit that to 1. And so that will then give me the youngest bike rider, because it'll give me the largest number and go all the way down to the smallest. And so this will give me the limit 1 will give me the top result. Excellent. Okay, so let's move on to the concept of indexes. So we can actually apply indexes into our database, into our collections that help speed up search times. So again, we'll just briefly mention this as a concept so you know it's a possibility in Mongo, but we won't spend too much time talking about this. So indexes make queries even more efficient. They are one of the most impactful ways to improve your query performance. An example of what an index is in terms of concepts is, think of it this way. In a book, an alphabetical list of names or subjects or whatever is given with reference to the places where they occur and are typically found at the end of the book. So if you look at the back of the book, usually there's an index that shows you how to flip very quickly in a book. So to give you an example of how you might find something in a book without using an index versus using an index, suppose you want to find all mentions of Toni Morrison in a book. You could just look through every page in the book, right? That would work, but it's slow. Or if you used an index, you might find all mentions of Toni Morrison by going to the M portion of the index in the back of the book, locate Morrison, and go to the reference pages. Much quicker way of finding that data in that book, right? And so conceptually, that's what we're doing with indexing in our database, where you can provide an index to speed up your searches. So again, in a database, a special data structure that stores a small portion of the collections data set in an easy to traverse form. So when might you want to index? Typically, you index to avoid sorting. So if you find yourself constantly having to sort the results of your queries, then that highlights a time where you might want to consider indexing off of those then. So imagine this, given your database, you have trips collection, you're trying to find a birth year of 1989, and in your database and your trips collection, you're trying to find some start station ID 476, and you're then sorting based off of this birth year. So here you're finding and then sorting based off this other thing. Well, this would be a time to use a query where you'd want to create an index based off of birth year, and then you don't have to sort for birth year. It can use these IDs and help isolate off of those birth years for you. So again, looking back at this previous example, the query that's going to take a long time is going to then be this find by birth year, whereas if we had created an index, I'm sorry, the one that takes less time is if we create an index by birth year and then we could just find. And the one that will take time is if we do this sort. Because if we use the sort with creating an index, it should be able to speed up our performance. Okay, let's see here. Now, there is the possibility that you can actually create compound indexes too, and that's just passing a collection of multiple indexes. So you might have like a start station ID and a birth year that you want to search on. And if that's the case, when you go to create a collection, an index, you can create a object, right, that has multiple fields and multiple values by which you want to create indexes with. And again, you just call the create index method on a collection, and you give it the field that you want to create indexes for in order to be able to use it. So, and then whenever you do a sort operation, it can use the indexes for those uses the index for the sort operations to speed that up. So an example here is, suppose you wanted to create an index on birth year, but you were finding based off of the start station ID and then sorting by the birth year. A compound index would allow you to create an index that uses both the start station ID and the birth year. And so what that would do effectively is, as opposed to having to search your documents like this, you can search them just like this. So you can see the amount of evaluations that have to occur to return back the results of your query are sped up. Now, again, this is just a conceptual thing. You probably will not have to use this, but it's just highlighting some of the optimization tricks you can do with Mongo to speed up its performances. Now, just to give you some examples of how this is done, that's what we just looked at. Okay, so just a quick conceptual quiz on how we might use this. Imagine if you have someone who's often querying the routes collection by the source airport field. So they're constantly trying to find the airport with the label MUC from the database. And if you want to quicken this up, you might want to index. And so how might you make that index? Would it be with the make index method? Would it be create index method and add index method or generate index? Well, clearly, there's only one method we saw on how to use indexing in this section as create index. And the value here doesn't matter. It could be either minus or positive when you create the index value. Okay. We talked mainly about how to query and how to create documents and how to read documents and how to update documents and a lot of really complex CRUD operations. Let's talk a little bit about data modeling, because that's something you'll actually be doing for your full stack application. So what is data modeling? It's a way to organize your fields in a document to support your application performance and querying capabilities. So those are the two considerations you have as you start to model out your data. So a general rule by which to follow for data modeling, data is stored in the way that it's used. So imagine that we had this patient one data. Imagine that this is a data for some medical application. Here, data that you would use might be the preferred contact, which might be like type, email, and the email address, or contact info, which might be like the work number, and then the actual number, the contact number, or it could be the cell number and that contact number. It could be the prescriptions for this patient. It could be the visit history of this patient, along with dates and notes and whatnot. So imagine if you had this patient one that had this data, all relevant towards this their patient history. But then we had this other patient where we had preferred contact email, right? And alternate contact information, and then no history yet, right? No prescriptions yet. So these both represent data that gets used inside your application. So some of the main considerations you might have for data modeling in this instance is, well, what are you going to store? In this instance, it's like contact information. It's your visit history, it's your prescriptions, the age, the gender, etc. And then the next thing you want to ask yourself is, how will it be queried? Like, who is using your application, and how's your application going to use that data for whatever operations or task it has to perform? So what the doctors may need, they might need the current prescriptions, they might need the diagnosis, they might need the patient contact info, or the ability to cross-reference the medication information like side effects or allergies or things like that. So these might be things you want to consider while you're building out your data structures or your data models for storing your data in your database. So again, you want to break it down into the concept of how do you organize the data versus how are you going to then query that data, right? Like, this is the ability to browse the data, to discover what's in the data, to access the data, and this is just the data that has to be maintained. Two different concepts, but both intimately important to one another for performing the operations effective of the database. So data modeling with MongoDB, data that is used together should be stored together. So an evolving application implies an evolving data model. And that's one of the nice things about MongoDB is that it's a document store, so you're essentially storing things in the form of JSONs. So imagine we had this problem just based off of the simple data modeling we talked about. What is data modeling? And choose the best answer. So only one of these four is correct. It's a way to organize fields in a document to support your application's performance and querying capabilities. Yeah, that sounds like it. It's not a way to show off your amazing data to anyone else in graphs or illustrations. A way to build your application based on how your data is stored. No, we should store our data in the way that our application will intend to use it. and a way to decide whether to store your data in a cloud or locally. No, this is a different consideration. So it's going to be this first one. It's just a way to organize fields in a document to support our application performance. Okay, let's talk about upserts, which is either updates or inserts. Yes, to that question, it is an update or an insert. It's both, depending on what it needs to be. So upsert, so everything in MQL that is used to locate a document in a collection can also be used to modify the document. So think about it this way. Imagine this update one with a query where we want a query to locate something, and then we have this ability to update, and that's the default. Well, there's this other parameter we can pass in the update method. So we have as our first parameter the query. The second parameter has been our update operator. The third parameter, which we will now talk about, is whether we want to set upsert to be true. By default, upset is set to false, which means that it only updates if the value is found and does nothing if the value is not found. But when upsert is set to true, if it doesn't find that value and update, then it will create it for you. So it acts as an insert. So it acts as an insert if it doesn't exist, and it acts as an update if it does exist. So effectively, is there a match? Then update the match document. Is there a match? No, then insert that new document. Okay, don't care about that. Okay, so the example that they give is one that uses smart home data, where you might have multiple sensors with multiple readings throughout your house. And so imagine that the collection that we're getting with our smart home data is like this ID object, a sensor number, the date by which we're getting a reading, the val count, and the total number of that, and then each of these readings. So the val count is the number of readings, and the total number is the total number of these values here. And the t is the time differential that this reading was taken. So at time 0, at time 5. Okay. So if we set upsert to be true in this instance, let's see how that might actually manifest itself in comparison. So how does upsert actually work? So imagine in this example I gave a moment ago, if there was no document when we go and do our update one, so we're going to do a sensor on this sensor with this date, and our update is to increment the val count to 1 and to set the total time. Well, if it doesn't exist, then it's now going to insert this object. This now current object now is sensor 5. It has an ID. It has this date. The val count is now set to 1. And the total is whatever the total sensor of the value is. But now if we go and do that upsert, if we do the update again with upsert to be true, and if it goes and says, hey, this document now exists, instead of doing the insert, it can now do the update. So the first, on an insert, this is the operation. On an update, it does the push operation. So on the initial insert, we did this increment. On the update, it does a push operator where it will push into the readings a value time. So now notice our document goes to having these fields to now having a readings field that now has a additional array attached to it. So this is an example of what happens to this document when it gets updated versus inserted, hence the term upserted. And yeah, so not a lot of detail. Again, just to let you know, this is a thing that exists. Quick problem just to know about and related to upserts. How does the upsert option work? Check all that apply. When upsert is set to true and the query predicate returns an empty cursor, the update operation creates a new document using the director for the query predicate and the update predicate. Yeah, this is true. That's the case. When upsert is set to false and the query predicate returns an empty cursor, then there will be no updated document as a result. Yep, that's also true, because if you're not doing upsert, if that's set to false, you're not going to insert. You only insert when upsert is set to true. So if it returns nothing, then you will create a document as long as upsert is set to true. If upsert is set to false, then it just updates. By default, Upsert is set to false, yes. That is true. So these three are true. Let's check this one. It is used with the update operator and needs to have its value specified every time that the update operator is called. No, that's not true. It only needs to be specified if you want to change the default false setting to true. Okay, so the final part of this set of slides, part 6, is next steps. Next steps really highlights a lot of Mongo technologies. I don't really care so much about this because this to me seems much more of letting you know what other services the Mongo provides to database. But really what those include are the Atlas features, which is more things beyond data or more on Data Explorer, other Atlas products and options, and then what is MongoDB Compass. And so here, I'm not really going to cover this information. I think this isn't really relevant towards using Mongo database, but it's on the certification test. So I give you the sample problems from the quizzes you might encounter from there. So I'm going to just skip past those and just let you know that those are available as a reference in this document. But that's it with Mongo. We are done. In 3 lectures, we covered everything that you need to know about Mongo as per even what Mongo thinks you should know. So at this stage, this part of the lab is to go to Mongo University, go get your Mongo certificate. They'll actually give you something that you can print out. It'll actually be digitally signed too, so it will always be yours. You could have a custom link that goes to something with your name and the date that you get that for, and that'll be what lab, what that next lab is. What is that, lab 13? I think that's lab 13, which is the Mongo lab. So please start on that now. I do want to say that it does take a little bit of time to get done, but using this document, this slide as your reference, you should be able to get through it relatively quickly. Excellent. With that said, is there any questions that anyone has as it relates to Mongo? Does this seem like a simple enough solution to be able to maintain the data for your full stack applications? Excellent. And so these slides are already available to you on Moodle, and I'll go ahead and upload both this video and the last lecture video. So you'll also have my my descriptions, all of my explanations on all these slides available to you as well. So next lecture, we will, I took the poll in Discord, and so I will be discussing REST APIs and microservice architectures, and then also WebSockets. And then we'll follow up with React. So let me just go ahead. If there's no other questions, I'll go ahead and stop the recording here, so it doesn't get too lengthy.